everyone, this is lecture 52 of the course on principles of behavioral economics. We have started discussing analytical game theory under the broad topic of strategic interactions. So, in the previous module we introduced the basic concepts related to game theory and also talked about how we derive the Nash equilibrium. Now, we are going to talk about another kind of game, very popular kind of game known as prisoner's dilemma. Similar to battle of sexes, I would also like to mention here that prisoner's dilemma, of course, here will be a classic case, but then from that classic example of prisoner's dilemma, now prisoner's dilemma has actually become a type of game which does not necessarily always imply that prisoners are involved. It's depending on the distribution of payoffs, certain games are now categorized as like the battle of sexes or the prisoner's dilemma, or there is stag hunt and so on. So, here let us talk about the classical example which gave birth to the concept or the idea of prisoner's dilemma games. Here two criminals are arrested on suspicion of two separate crimes. The prosecutor has sufficient evidence to convict the two on the minor charge, but not the major one. If the two criminals cooperate with each other and stay mum, they will be convicted on the minor charge and serve 2 years in jail. First of all, the criminals are arrested on suspicion of two separate crimes, one is a major one, another is a minor one. Now, we are saying that there are two strategies. The first one is cooperation with each other, where both of them will just stay mum, would say that no, I have not done it and that is it. So, they will not be able to convicted of the major one, only for the minor one they will serve 2 years in jail. The prosecutor offers each one of them a reduced sentence if they defect, that is testify against the other. So, here the situation of defection that we defined in the previous module, where one can defect and then get benefit at the cost of other. So, here defection implies that one prisoner or one criminal would say that I have not done it, but the other fellow has done it. So, just because he has testified against the other criminal will get actually 20 years of jail, 20 years in jail, while the person who defects says that I have not done, but the other one has done, actually goes free. So, if one prisoner defects but the other one cooperates, so while one prisoner is saying the other one is doing, the other one is saying no, I have not done. So, then the defector goes free, whereas the cooperator serves 20 years in jail. If both defect, that is both of them say that the other one has done, but I have not done, both get convicted on the major charge, but as a reward of testifying only serve 10 years in jail. Assume that each prisoner cares about nothing but the number of years he himself spends in jail. So, there is no empathy, sympathy for the other one. You just think about yourself, and then let us see what would be the Nash equilibrium in this case. So, what is the first of all payoff matrix, and then what is the Nash equilibrium? So, if I mention the years in jail as negative payoff, and when someone is set free then the payoff is 0, we can have any kind of numbers in this situation. We can have also positive numbers instead of 0 when someone is set free. Then this can be considered as a payoff matrix, where when both players are cooperating, that is both of them are keeping quiet, then they are serving jail terms just for the minor complaint. So, 2 years of jail or minor crime, so 2 years of jail. But suppose player 1 keeps quiet while player 2 defects, then player 2 goes free and player 1 serves a jail term of 20 years. Similarly, if player 2 keeps quiet and player 1 says the other fellow has done it, I have not done, then player 1 goes free while player 2 serves jail term of 20 years. And if both of them say that I have not done, but the other one has done, then both of them serve a jail term of 10 years. So, minus 10 minus 10. And how do we obtain the Nash equilibrium? As you can see that if player 1 cooperates, then player 2 is better off by defecting. If player 1 defects, then by comparing minus 20 and minus 10, again player 2 is better off by defecting. when player 1 cooperates, then player 2 cooperates, then player 1 is better off by defecting, because I am now comparing minus 2 with 0, and when player 2 defects, then again by comparing minus 20 and minus 10, player 1 is better off by defecting. So, defect is the Nash equilibrium. Now, here we talk about something called a dominant strategy. A strategy X is said to strictly dominate another strategy Y if choosing X is better than choosing Y, no matter what the other player does. So, here you can see that for each strategy of player 1, player 2 is better off by defecting. Player 2 is better off by defecting minus 20, minus 2 and 0, minus 20 and 10. So, defect is the dominant strategy for player 2. For each strategy of player 2, you can see that minus 20, minus 2, minus 20 for each strategy of player 2. So, for cooperate, this is like minus 2 and 0, so 0, and for defect minus 2 and minus 10, so minus 10. So, again defect is the dominant strategy for player 1. In the prisoner's dilemma, defection strictly dominates cooperation, so cooperation can be eliminated altogether. No rational player will cooperate and both will defect. Pareto dominate outcome or strategy in this context is defined as an outcome X that is said to Pareto dominate another Y if all players weakly prefer X to Y and at least one player strictly prefers X to Y. And the related concept is that of Pareto optimal outcome or strategy. An outcome is Pareto optimal if it is not Pareto dominated by any other outcome. Alternatively, an outcome is Pareto optimal if it is a Pareto dominant strategy. In the prisoner's dilemma, the cooperative outcome CC Pareto dominates the Nash equilibrium DD, because you can see that the Nash equilibrium is minus 10-10. Defect are definitely dominant strategy, but they are not Pareto optimal outcome or Pareto optimal strategy, because Pareto optimal outcome is an outcome where both of them would be better off. So, cooperative outcome Pareto dominates the Nash equilibrium DD. That's why at times considered to refute Adam Smith's insight that the rational pursuit of individual self-interest leads to socially desirable outcomes. Individual pursuits are leading to a dominant strategy of defect and this is the outcome, while the socially desirable, that is both of them together, would have been benefited by an outcome like or strategy profile like cooperate and outcome like minus 2-2. So, this is a situation where Adam Smith's insight that the rational pursuit of individual self-interest leads to socially desirable outcome is refuted. As I probably mentioned in the beginning of the strategic interactions, that it has been actually observed that in the context of analytical game, it need not be always true. Now, we talk about game with no Nash equilibrium in pure strategy. Suppose you want to study in the library or in the department, but do not want to run into your bestie. However, your bestie would like to study with you. So, you want to study alone while your best friend wants to study with you. Now, there is a conflict of interest and see what happens. Suppose a player gets a utility of 1 whenever his or her goal is attained and 0 otherwise. So, your goal is to study alone. If you get to study alone, then you will be getting a utility of 1. Your bestie's goal is to study with you, and if she gets to study with you, then she will get a utility of 1. In case you do not get to study alone, your utility would be or payoff would be 0, and if she does not get to study with you, then her payoff or utility would be 0. So, this is how we construct the payoff matrix. We are measuring this is player 1 and bestie is player 2. The two options are where to study, library or department, for both of you, library or department. So, if you happen to be in library and your best friend is also in library, so basically you two are studying together, your goal is not fulfilled, you are getting a utility of 0, your best friend is getting a utility of 1 because that is what she wanted to do. But if you are in library and she is in department, or your best friend he is in department, then you are getting your goal is fulfilled, you are in two different places and you are getting utility of 1 while she is getting 0. In a similar fashion, you can understand that when you two are in different places, you are happy getting a utility of 1 and she is getting 0. When you two are at the same place, then you are not happy getting a utility of 0 and she is getting a payoff of 1. So, what is the Nash equilibrium here? Now, you can see that if we try to find out the Nash equilibrium, when you are in library, it is best for her to be in library. I am comparing 1 and 0. When you are in department, then it is best for her to be in the department. When she is in the department, then it is best for you, by comparing this two, to be in the department. When she is in department, then again it is in your best interest to be in the library. So, we do not have any Nash equilibrium here, understandably, because what is best for you is not judged to be best for her by herself. So, there is no Nash equilibrium in this game. These games are also known as matching pennies, where two players flip two coins. If both get head or tail, player 1 wins, otherwise player 2 wins. So, in case both of them, basically both of them toss a coin, and if both of them get the same thing, either head or tail, then it is for player 1 to win. If they get different things, like one gets head, another gets tail, or one gets tail, the other gets head, then this is for player 2 to win. So, again there is a conflict of interest. Only one of these two can happen, both of them cannot happen together. So, in one situation one wins, in the other situation the other fellow wins. So, these games are pretty close to what is known as the zero sum game. Ideally, a zero sum game should have payoffs like -1 1 and 1 -1, so that for each and in each and every cell the payoffs are getting summed up to 0. But what it implies is that there is a conflict of interest. What is good for you is not good for the other fellow. What is good for the other fellow is not good for you. So, from that perspective, these are also zero sum game, or pretty close to the type of zero sum game. A zero sum game is a game in which the gains and losses of the individuals sum to 0 for all combinations of strategies they might pursue. Okay, so what we have seen is that some games have no Nash equilibria in pure strategies, but that does not mean that they do not have Nash equilibria. So, pure strategies are like when you are choosing more or one or more of the strategies that appear to be the best possible strategy for you. But mixed strategies are essentially while you are combining the pure strategies with certain probabilities. In the study example, as we saw that the game did not have any Nash equilibrium. The game does, however, have a Nash equilibrium in mixed strategies. Suppose that you figure out where to go by flipping a coin, and that your bestie does the same. Given that you have a 50% chance of ending up at library and a 50% chance of ending up at department, your bestie is indifferent between library and department and can do no better than flipping a coin. Basically, since both of you do not have any idea about where the other person is going, you are actually indifferent between the two locations. So, you can decide just by flipping a coin that where to go. And given that your bestie has a 50% chance of ending up at library and a 50% chance of ending up at department, you are indifferent between library and department and can do no better than flipping a coin. The two of you are in a Nash equilibrium, though you are playing mixed rather than pure strategy. So, here the two strategies are library and department for both of you. And since you are flipping coin to decide where to go, we say that you are using a mixed strategy with each strategy having a 50% chance of occurrence. In a game like this, the mixed strategy equilibrium is easy to find. In other games, it can be more tricky. Now, let us consider the game of battle of sexes. Assume that the wife has a probability of P going to the concert and 1 minus P of going to the theatre. So, the wife goes to the concert with the probability of P, to the theatre with 1 minus P. The probabilities for the husband are Q and 1 minus Q respectively. The players must be indifferent between the two strategies. Again, the strategies, they themselves do not tell you anything. So, when they are indifferent between the two strategies, which means that utility from concert is equal to utility from theatre. So, U concert is equal to U theatre for both of them. Now, equating U concert with U theatre, the values of P and Q can be estimated. How? The expected payoff of player 1 for each strategy are expected value of U concert, that is expected payoff of player 1 for each strategy. So, let us consider the first strategy like concert. So, expected payoff from concert is like if she goes to concert, then what are the probabilities of getting these payoffs? The probability is Q and the probability is 1 minus Q. So, she gets 2 utils of utility with the probability of Q and 0 utils of utility with the probability of 1 minus Q. Similarly, the expected payoff from theatre is 0 with the probability of Q and 1 with the probability of 1 minus Q. Now, since we say that these two are equal, so we equalize these two, 2Q into 0 into 1 minus Q, which is basically 2Q, would be equal to, this is again 0 and this is 1 minus Q, which gives me Q equals to 1 upon 3. So, equating them, we obtain Q equals to 1 upon 3. In a similar fashion, P can be calculated as 2 upon 3. So, in order to get P value, what we do? For each strategy of husband, the husband will see that he can get 1 with the probability of P and 0 with the probability of 1 minus P. So, he writes P plus 0 into 1 minus P is basically 0. This is equal to, which is basically the utility from concert for the husband, is equal to 0 into, this is for husband. So, this is 0 into P and 2 into 1 minus P. So, again 0 into P is 0 and 2 into 1 minus P, which implies P is equal to 2 by 3. I take 2P to the other side. So, this is how we calculate P. There is a Nash equilibrium in mixed strategies in which player 1 chooses concert with probability 2 by 3 and player 2 chooses concert with probability 1 by 3. In the mixed strategy equilibrium, player 1 gets payoff, which is UC equals to UT equals to 2Q and then that is 2 upon 3. Player 2 gets payoff again equals to 2 upon 3. This example shows that the games with pure strategy equilibria may also have mixed equilibria. Now, let us take some example. What will be the pennies in the following games or Nash equilibrium? So, if we consider pure strategy Nash equilibrium, then you can see that for U, player 2 chooses L, for D, player 2 chooses R. For when player 2 chooses R or for the strategy of L, player 1 chooses U, when 2 chooses R, player 1 chooses 2. So, UL and DR, UL and DR are the two Nash equilibria. We can also in a similar fashion calculate the mixed strategy equilibrium. Mixed strategy equilibrium would be calculated as Q equals to 1 upon 5 and P equals to 4 upon 5. This is another game. Now, you see here, if 1 goes for U, 2 goes for L. If 1 goes for D, then 2 is indifferent between L and R. If 2 goes for L, then 1 is better off by going for U. If 2 goes for R, then 1 would be indifferent between U and D. So, here you can see that UL and DR are again the two Nash equilibria, but if you try to calculate a mixed strategy equilibrium, you understandably can find none because most of the payoffs are 0. So, let us talk about pure versus mixed equilibria. Although mixed strategy equilibrium may at first seem like an artificial construct of mainly academic interest, mixed strategies are important and common in a wide variety of strategic interactions. Even if you are a tennis player with a killer cross-court shot, it would be unwise to hit the cross-court shot every time or your opponent will learn to expect it. Every so often you must hit the ball down the line. In games like this, in order to keep your opponent guessing, you must mix it up a bit. This analysis shows that it is not a mistake but necessary every so often to hit your weaker shot. So, basically even though you have a very clear Nash equilibrium of playing the best shot you can, but then if you keep on playing that particular shot, then you would be very easily guessed and your opponent might have an upper hand, and as a result of which you need to play actually mixed strategies sometimes, that is there are certain probabilities that you would be playing certain shots. In games, the fact that a person chooses the inferior option from time to time does not mean that he or she is not playing an equilibrium strategy. According to the authors of the book Spousonomics, Paula Schwarzman and Jenny Anderson, economics is the surest logical solutions to what can often seem like thorny, illogical and highly emotional domestic disputes. Suppose that you are stuck in an equilibrium where you do the dishes, make the bed and empty the cat litter while your spouse sits back and relaxes. Spousonomics apparently teaches that you can turn your spouse into an acceptable partner by playing a mixed strategy, by sometimes doing the laundry, sometimes not, sometimes making the bed, sometimes not, and so on. So, even though relaxing is the best strategy for you, in pure strategy relaxing gives you the maximum Nash equilibrium, a maximum payoff, and it is a pure strategy Nash equilibrium when you just relax and your wife does everything. But then that leads to a lot of conflict, and in order to avoid that you can always go for a mixed strategy, sometimes doing certain things, so that there is less of animosity between you and your spouse. Similarly, let us take the example of chess. Chess is a finite game. We know this because every player has a finite number of moves to choose from at any point in the game, and because every game ends after a finite number of moves. Because it is a finite game, Nash's theorem establishes that it has an equilibrium. This suggests that chess should be uninteresting, at least when played by experienced players. Assuming player 1 plays the equilibrium strategy, player 2 can do no better than playing the equilibrium strategy and vice versa, and they are very much predictable, as a result of which the game becomes uninteresting. Thus, we should expect experienced players to implement their equilibrium strategies every time and the outcome to be familiar and predictable. Yet, Nash's theorem only establishes the existence of an equilibrium. It does not reveal what the equilibrium strategies are. As of yet, no computer is powerful enough to figure out what they are. And even if we knew what the strategies were, they might be too complex for human beings to implement. Thus, chess is likely to remain interesting for a good long time. And finally, we talk about Nash's theorem. So, what Nash's theorem says is that every finite game, that is every game in which all players have a finite number of pure strategies, has a Nash equilibrium. Given this theorem, the search for Nash equilibria is not futile. As long as the number of pure strategies available to each player is finite, and whether this condition is satisfied is fairly easy to determine, we know that the game has at least one Nash equilibrium in pure or mixed strategies. That is neat. So, I conclude this module with this note. In the next, we are going to briefly introduce the extensive form game, and we will talk about the types of game. These are the references for this module. Thank you.